Welcome to Ultimate Sleep Doctor. Tonight, we turn our attention to something truly extraordinary, the raw power of the sky. Lightning, a fleeting dance of energy, a visible whisper of the universe's vastness. It's a spectacle born of atmospheric conditions, a testament to the incredible forces at play above us. Consider for a moment the sheer volume of electrical charge involved, the heat, the brilliance. These bursts of energy have shaped our planet and continue to hold a certain, undeniable mystery. If you find these explorations soothing, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. Just breathe, let your thoughts drift. Let's begin. The sky, a vast canvas of deepening blue, wasn't always a tranquil expanse. Before the clouds settled, a restless energy danced, a silent struggle happening high above us, the creation of a lightning leader. It wasn't a sudden burst of fury, but a careful, step-by-step process, a delicate negotiation with the air itself. Understanding how this happens begins with a crucial stage, the breakdown of the ionosphere. The ionosphere isn't a solid layer like the Earth's crust. It's a complex region of the upper atmosphere, extending roughly from 60 kilometers up to around 1,000 kilometers above us. This region is characterized by a significant population of ions, electrically charged atoms and molecules, largely due to the constant bombardment of solar radiation from the sun. This solar radiation, particularly ultraviolet light, carries enough energy to strip electrons away from atoms in the air, creating this charged environment. The air itself, under normal circumstances, is surprisingly cooperative. It acts as a rather good insulator, resisting the flow of electricity. Think of it like a very dense sponge. It holds onto its electrons tightly. However, when enough energy is concentrated in a small area, this resistance can be overcome. This is where the ionosphere becomes vitally involved. The ionization created by the sun is not uniform. There are areas where the concentration of ions is much higher than others, created by intense solar flares, the reflection of sunlight, or even just variations in atmospheric density. These regions of enhanced ionization are like tiny stepping stones, ready to be triggered. The process begins with a downward-pointing discharge, often referred to as a stepped leader. This isn't a single, instantaneous jolt. It's a series of discrete, rapidly propagating channels of ionized air. The initial step, typically a few centimeters in length, is driven by a process called corona discharge. Corona discharge is triggered when a sufficiently high electric field builds up within a localized region. This electric field isn't created by a main lightning strike yet. It's a preliminary buildup, a silent accumulation of potential difference. Within this localized area of intensified ionization, the already abundant ions, primarily positive ions, are accelerated by the electric field. These accelerated ions collide with neutral air molecules, effectively pushing them along, creating a channel of highly ionized air. The key here is the stepped nature. This channel isn't continuous. It breaks up and reforms repeatedly as it advances downwards. Each step is only about 50 to 100 meters long, and it takes only a thousandth of a second to form. The reason for this breakdown and reformation is crucial. It's related to the delicate balance between the electric field and the ionized air itself. As the stepped leader extends downward, the electric field strength weakens. This weakening, in turn, reduces the acceleration of the ions, leading to the breakdown of the ionized channel. The channel then reforms as the electric field builds up again, ready for the next step. Importantly, the stepped leader isn't just randomly extending downwards. It's guided, in a sense, by the path of least resistance, seeking out regions of higher ionization within the ionosphere. This is heavily influenced by the presence of large-scale electric fields generated by thunderstorms, which are themselves formed by the upward movement of charged air. The stepped leader essentially follows these electric field lines. The ionosphere acts like a conductor, guiding the formation of the channel. The higher the concentration of ions along a particular path, the more readily that path will be established. Now, let's consider the role of the ionosphere's density variations. The ionospheric density isn't uniform. It fluctuates significantly, particularly in response to solar activity. Intense solar flares, for instance, dramatically increase the ionization in the lower ionosphere, making it far easier for a stepped leader to initiate and propagate. This explains why lightning strikes are more frequent during periods of heightened solar activity. Conversely, during periods of low solar activity, the ionosphere is less dense, and it takes much more energy to initiate a stepped leader. The propagation of the stepped leader isn't a smooth, continuous movement. It's characterized by a dart, a sudden, rapid advance of approximately 30 meters in just 50 microseconds. This dart is followed by a pause, a period of about 100 microseconds during which the channel begins to break down. This alternating pattern of darting and pausing continues until the stepped leader reaches a sufficient distance, typically around 10 kilometers, from the negatively charged cloud below. At this point, the stepped leader makes contact with the negatively charged cloud. Almost instantly, a return stroke, a brilliant, upward-moving discharge begins, carrying the accumulated charge back to the cloud. This return stroke is what we actually see as lightning, appearing as a bright flash as the electrons rapidly move back to their origin. The stepped leader provided the initial pathway, but the return stroke is the spectacular, visible manifestation of the completed electrical discharge. The entire process, from the initial breakdown within the ionosphere to the return stroke, happens incredibly fast. It's a chain reaction of ionization, acceleration, and discharge, all governed by the fundamental laws of electromagnetism. The ionosphere, therefore, isn't simply a passive backdrop to lightning. It's an active participant, playing a critical role in the formation and propagation of this awe-inspiring natural phenomenon. Understanding this step-by-step process gives us a deeper appreciation for the complex and beautiful workings of the sky above. The sky, even on a seemingly calm day, holds a tremendous amount of electrical potential, a constant, subtle dance of charge. While the stepped leader formation, that initial jagged connection to the ground, is crucial for initiating a lightning strike, it's not the whole story of how lightning happens. Understanding why this charge separation occurs is equally fascinating. It's not a simple, static process. It's a dynamic, turbulent struggle between competing forces within the atmosphere. The key to this struggle lies in atmospheric convection and the presence of shear, differences in wind speed and direction, high above the clouds. Consider the air itself. It's not uniform. Warm, moist air near the surface rises, creating updrafts. These updrafts aren't gentle breezes, they're powerful currents of air, driven by the sun's heating of the ground and the evaporation of water. As this warm, moist air ascends, it carries with it a significant amount of water vapor and, crucially, aerosols, tiny particles like dust, salt, and pollutants. These aerosols act as condensation nuclei, providing surfaces for water vapor to condense and freeze upon. This process is called ice crystal formation, and it's a fundamental element in the development of thunderstorm clouds. Now, imagine that this rising air isn't moving in a straight line. Instead, it's swept along by large-scale winds, jet streams, for instance, that can extend hundreds of kilometers into the atmosphere. These winds create horizontal shear. Shear describes the change in wind speed and/or direction over a relatively short distance. This is where things get complicated and where the true power of charge separation begins to emerge. Different layers of air, moving at different speeds and in different directions, begin to jostle and rub against each other. The rising, updrafting air, laden with ice crystals and aerosols, is particularly vulnerable to this shear. Because it's rising rapidly, the air itself is constantly being stretched and distorted. This stretching doesn't just affect the air's shape, it also profoundly alters the electric properties of the air. The rapid movement of air molecules creates regions of compression and rarefaction, areas where the air is squeezed together and expanded, respectively. These changes in density have a direct impact on the electric field, causing a separation of charges. Specifically, the faster the air is moving, the greater the distortion of the electric field. When air moves rapidly upwards, it tends to carry a positive charge. This is because the higher speeds compress the air, increasing its ability to hold positive charges. Conversely, the slower moving air moving horizontally tends to carry a negative charge. The interplay between these ascending, positively charged currents and the horizontally moving, negatively charged currents generates a strong electrical field. The presence of ice crystals within the clouds significantly amplifies this effect. Ice crystals themselves possess a bipolar electric charge, meaning they have both a positive and a negative end. As these ice crystals collide with each other within the turbulent environment, they exchange charge. Generally, the larger, heavier ice crystals tend to acquire a net negative charge, while the smaller, lighter ice crystals acquire a net positive charge. This further contributes to the overall charge separation, intensifying the electrical field. The shape of the thunderstorm cloud itself plays a vital role. Thunderstorms are rarely perfectly symmetrical. They often have complex, distorted shapes. These irregularities, convective cells, anvil tops, provide pathways for the charged air to flow and interact. The anvil, in particular, is a region of highly sheared, outflowing air. The air within the anvil is moving at significantly different speeds and directions compared to the surrounding atmosphere, creating a substantial shear zone. This shear is believed to be a primary driver of charge buildup in the anvil. Furthermore, the interaction between the strong updrafts and the outflowing downdrafts, the mesoscale circulation within the storm, contributes to the process. As the updraft carries positively charged air upwards, it encounters the negatively charged outflowing air, creating a zone of intense electric field. This zone can become so strong that it overcomes the air's resistance to movement, leading to the formation of stepped leader channels. It's a continuous feedback loop. The shear creates the electrical field enhances the shear, and so on. The distribution of charge within the storm isn't uniform either. The top of the storm, particularly the anvil, typically holds a strong positive charge, while the lower portion of the cloud tends to be negatively charged. This asymmetry is related to the complex interplay of updrafts, downdrafts, and the overall circulation patterns. Scientists continue to refine their models to better understand the precise mechanisms governing charge distribution. Understanding atmospheric charge separation through convection and shear is paramount to predicting lightning formation. By recognizing the influence of these large-scale atmospheric processes, we can gain a deeper appreciation for the tremendous power contained within a thunderstorm and the delicate balance that allows a seemingly random discharge to occur. It's a stunning example of how seemingly simple physical principles, rapid air movement, temperature differences, and the properties of water can combine to create one of nature's most dramatic displays. The vastness of a thunderstorm isn't just about the dramatic flash of lightning. It's a surprisingly intricate dance of frozen water and charged particles. While the initial buildup of negative charge in the lower atmosphere is often attributed to simpler convection and updraft processes, the precise mechanism for transferring that charge, for turning that initial negative charge into the powerful electrical discharge we see, relies heavily on the behavior of ice crystals within the storm's towering cumulonimbus clouds. These aren't just passive bystanders. They're key players in a fascinating process that's still being actively researched and refined by scientists. Within the heart of a cumulonimbus cloud, temperatures plummet to incredibly low levels, often far below -40 degrees Celsius. At these frigid temperatures, supercooled water droplets of water that remains liquid even below its freezing point are abundant. These droplets, surrounded by warmer air, exist in a state of delicate equilibrium. But when these supercooled droplets encounter ice crystals, a change begins. The ice crystals, formed through the freezing of water vapor, act as tiny, jagged electrodes, capable of attracting and holding a static electric charge. The most common type of ice crystal involved in this process is graupel. Graupel is essentially soft hail, small, loosely packed balls of ice. It forms when supercooled water droplets freeze onto an ice crystal nucleus. As these water droplets freeze, they grow rapidly, accumulating more and more supercooled water. The surface of graupel is remarkably rough, covered with a multitude of tiny grooves and pits. This roughness is absolutely critical to the charge transfer process. The jagged edges and imperfections on the Graupel's surface create an enormous number of points where charge can accumulate and be redistributed. But Graupel isn't the only ice type playing a role. Larger hail, composed of layers of ice accreted over time, also contributes significantly to the electrical activity within the cloud. Each new layer of ice that forms on a hailstone acts as another potential surface for charge separation. The process of ice accretion itself, where supercooled water freezes onto a pre-existing ice crystal, is believed to be intimately linked to charge transfer. As water freezes onto the hailstone, it's thought to create a slight separation of charge, with the outer layers acquiring a net negative charge and the inner layers retaining a more positive charge. The exact reasons for this charge polarization are still debated, but the rough, layered structure of the hailstone is undoubtedly a crucial factor. The mechanism for this charge transfer is still not fully understood, but scientists believe it involves collisions between the ice crystals and the surrounding air. As ice crystals move within the turbulent updrafts of the thunderstorm, they collide with air molecules, carrying with them a charge. The rough surfaces of the Graupel and hailstones then act as collectors, attracting and concentrating these charges. Think of it like a tiny, natural Van de Graaff generator, repeatedly accumulating charge through countless collisions. This isn't a simple, one-way transfer. The movement of the ice crystals themselves, swirling and jostling within the cloud, dramatically influences the distribution of charge. The turbulent air currents within the storm create a chaotic dance of ice crystals, constantly colliding with each other and with the surrounding air. This constant bombardment is what allows the charge to be effectively separated. The negative charge tends to concentrate on the larger, more complex particles, the Graupel and hail, while the positive charge remains more evenly distributed in the surrounding air. It's a self-organizing process, driven by the physical movement of the ice crystals. Furthermore, the presence of liquid water within the cloud also plays a role. The water droplets act as a conductor, facilitating the movement of charge. As the ice crystals collide with the water, the charge can be conducted across the interface, further contributing to the overall charge separation. The distribution of liquid water isn't uniform. It tends to concentrate around the edges of the ice crystals, which again amplifies the electrical effects. The development of strong electric fields within the thunderstorm is then a direct consequence of this organized charge separation. The negative charge concentrated in the lower part of the cloud and the positive charge in the upper part creates an immense potential difference. This difference in potential is what drives the lightning discharge, the spectacular release of energy that we witness. Modeling these complex interactions, the movement of ice crystals, the distribution of charge, and the formation of electric fields is an incredibly challenging task. Scientists use sophisticated computer simulations to try to replicate these processes. These simulations often incorporate detailed representations of ice crystal properties, turbulence, and fluid dynamics. The accuracy of these models is constantly improving, As we gather more observational data from aircraft and ground-based instruments. Radar observations, for example, are invaluable in tracking the movement of ice crystals within thunderstorms. By analyzing the echoes reflected by these crystals, scientists can gain a better understanding of their behavior and their contribution to the electrical activity. Similarly, specialized probes equipped with sensors designed to measure electric fields and charge densities provide critical data for validating and refining these models. It's important to remember that lightning isn't just about a sudden, explosive discharge. It's the culmination of a gradual, ongoing process, a precisely orchestrated dance of frozen water and charged particles that has been shaping our atmosphere for billions of years. The next time you see a flash of lightning, take a moment to appreciate the incredibly intricate and fascinating physics that lies behind this magnificent display of nature's power. The quest to understand lightning wasn't always a race against the storm itself. For much of its history, the lightning flash was simply a terrifying, unpredictable force. But humans, ever curious and driven by both fear and fascination, began to develop methods to detect and eventually predict these dramatic electrical events. The earliest attempts were surprisingly ingenious, born from a desire to mitigate the damage caused by lightning strikes to telegraph lines. In the mid-19th century, as the telegraph network expanded across North America and Europe, operators noticed a troubling phenomenon. Flashes of light, often mistaken for lightning itself, were disrupting communication. These weren't lightning strikes, though they resembled them. They were caused by the electrical discharge through the iron conductors of the telegraph wires. The rapid heating of the wire during a lightning strike created a localized ionization, producing a secondary, visible arc. This prompted inventors to develop what became known as lightning rods, metallic devices, typically made of copper or brass, strategically placed on buildings to intercept a strike and conduct the current safely to the ground. While not a detection system in the modern sense, these rods represented the first significant step towards understanding and mitigating the impact of lightning. The desire to truly know where lightning was occurring led to the development of lightning location systems, primarily in the late 19th and early 20th centuries. These systems relied on optical methods, essentially, watching for the brief flashes of light produced by a lightning strike. The most notable of these was the Schultz-Smith lightning indicator, invented in 1880 by German physicist Professor Hermann Schultz-Smith. This system employed a rotating drum covered with a series of concentric rings. As a lightning strike occurred, the rotation of the drum would be momentarily affected by the electromagnetic pulse emitted by the discharge. Sensitive mechanisms linked to the drum's rotation would then mechanically record the location of the strike on a map. While effective in identifying the direction of a strike, the system was notoriously unreliable, dependent on visibility and susceptible to interference from other electrical phenomena. The advent of radio technology in the early 20th century dramatically altered the landscape of lightning detection. Initially, radio detection relied on receiving the radio frequency signals generated by lightning discharges. These signals, known as sprites or flashes, were briefly emitted as the lightning channel interacted with the ionosphere. Early receivers were simple, essentially tuned circuits capable of detecting these bursts of energy. However, the signals were often weak and obscured by background noise. Research into the characteristics of these radio signals revealed valuable information about the height and shape of the lightning channel, significantly improving the accuracy of location determination. More sophisticated systems, developed throughout the 20th century, incorporated directional antennas and advanced signal processing techniques, allowing for real-time tracking of lightning strikes across vast distances. The 1980s witnessed a truly groundbreaking advance with the development of pulsed radar systems, specifically designed for lightning detection. Unlike continuous wave radar, these systems transmit extremely short bursts of radio energy pulses and then analyze the reflected signals. The brief duration of the pulses allows them to see the lightning channel, which is far more compact and reflective than the surrounding atmosphere. Furthermore, by analyzing the Doppler shift of the reflected signal, scientists can determine not just the location, but also the speed of the lightning channel's movement. This information is vital for predicting the path of subsequent lightning strikes, a crucial capability for aviation safety. These radar systems have evolved tremendously, becoming significantly smaller and more powerful, now routinely used by weather services worldwide. Beyond ground-based radar and radio detection, satellite observations have provided a complementary perspective on lightning. Satellites equipped with specialized sensors can detect the return strokes, the powerful discharges that occur within the main lightning channel that propagate upwards into the mesosphere and ionosphere. These upward strokes, often called sprites, enhancements, and TLEs, transient luminous events, were initially observed serendipitously during satellite operations, but have since become a major focus of research. Optical and infrared sensors onboard satellites can detect the heat signatures emitted by these events, providing invaluable data about their altitude, intensity, and relationship to the main lightning strike. The convergence of these technologies, ground-based radar, radio detection, and satellite observations, has dramatically improved our ability to detect, track, and understand lightning. Current systems are not just about locating strikes. They're gathering data that helps us refine our models of thunderstorm development and improve forecasting. The data collected is also informing research into the fundamental physics of lightning itself, furthering our understanding of the complex electrical processes occurring within these awe-inspiring and potentially destructive events. As technology continues to advance, we can expect even more sophisticated lightning detection systems to emerge, providing an ever more detailed picture of the electrical dance happening high above us. The vast, churning skies above are filled with incredible energy, a constant dance of electrical charges. While we've explored how this charge builds up within thunderstorms and how ice particles and graupel contribute to the sparking we call lightning, a very different kind of challenge emerges when that lightning gets close to something else, specifically an aircraft soaring through the clouds. The interactions between lightning and aircraft are a complex and serious concern. stemming from several distinct effects, each demanding careful consideration and increasingly sophisticated mitigation strategies. The most immediately apparent damage comes from direct strikes. Lightning isn't a gentle flicker. It's a colossal discharge of energy, often traveling along paths of least resistance. Aircraft, particularly those flying through actively charged thunderstorms, become surprisingly attractive targets. The metallic skin of an aircraft, designed to conduct electricity, provides a relatively easy pathway for the current to flow. When lightning strikes directly, the heat generated is astonishing. We're talking about temperatures reaching upwards of 35,000 degrees Celsius, hotter than the surface of the sun. This intense heat can cause immediate and catastrophic damage, melting away portions of the aircraft's skin, structural components, and even electronic systems. The force of the strike itself, the pressure wave created by the rapid expansion of air, can also inflict serious damage, potentially shattering windows, dislodging panels, and compromising the structural integrity of the aircraft. The severity of the damage depends heavily on the intensity of the lightning strike, the angle of impact, and the aircraft's construction. Some aircraft have been rendered completely unusable after a direct hit, while others have sustained significant damage that required extensive repairs. However, direct strikes aren't the only way lightning impacts aircraft. A more subtle but equally problematic effect is electromagnetic interference, or EMI. Lightning discharges generate enormous electromagnetic fields. As the immense current surges through the atmosphere, it creates a complex and fluctuating electromagnetic environment. An aircraft, with its multitude of electronic systems, navigation instruments, communication equipment, radar, and flight control computers, is exceptionally vulnerable to this interference. The electromagnetic pulses generated by lightning can corrupt data, disrupt communication signals, and even cause malfunctions in critical systems. Imagine trying to use a GPS device when the surrounding electromagnetic noise is overwhelming. That's a simplified version of what's happening within an aircraft during a lightning storm. The level of EMI experienced depends on the proximity to the lightning strike, the aircraft's shielding, and the sensitivity of its electronic systems. Some aircraft are specifically designed with enhanced shielding to minimize EMI, but complete protection is incredibly challenging to achieve. Researchers have identified a phenomenon called lightning strike arcs, which adds another layer of complexity to the threat. These arcs are essentially electrical pathways that extend outwards from a direct lightning strike. Instead of a single, immediate channel of current, the initial surge can create a series of branching electrical paths, potentially reaching out several kilometers. These arcs aren't always intense enough to cause immediate, catastrophic damage, but they can still induce significant EMI, causing temporary malfunctions and requiring pilots to take precautionary measures. The behavior of these arcs is still an area of ongoing research, as their formation and propagation are influenced by factors like atmospheric conditions and the geometry of the surrounding airspace. Mitigation strategies for aircraft operating in thunderstorms are therefore multifaceted. One crucial approach involves careful route planning. Pilots are trained to avoid areas with high lightning activity, utilizing weather radar data and storm reports to steer clear of the most intense zones. However, in certain situations, flying through a thunderstorm might be unavoidable, perhaps due to a routing requirement or a medical emergency. In these cases, several protective measures are employed. Aircraft often have lightning masts, tall, conductive rods mounted on the fuselage. These masts are designed to intercept a lightning strike, providing a preferred path for the current to flow around the aircraft, protecting the more vulnerable skin. The current is channeled downwards into the earth, effectively diverting it away from the aircraft's structure. Furthermore, aircraft are equipped with surge suppressors, electronic devices that clamp down on sudden voltage spikes, protecting sensitive electronic components from damage. These devices act as a sort of electrical buffer, absorbing and diverting the energy of a transient surge. The effectiveness of surge suppressors is constantly being evaluated and improved upon, as lightning events become increasingly complex and unpredictable. The ongoing development of sophisticated radar systems, both ground-based and airborne, plays a vital role in detecting and tracking lightning activity. These systems provide pilots with real-time information about the location and intensity of storms, allowing them to make informed decisions and take evasive action. Research into advanced materials for aircraft construction is also a key area. Materials with enhanced conductivity and shielding properties are being investigated to further reduce the risk of damage. Ultimately, operating aircraft safely in thunderstorms is a balancing act, a continuous effort to minimize risk while maintaining operational capabilities. The interactions between lightning and aircraft remain a technically demanding challenge, requiring ongoing innovation, meticulous planning, and a deep understanding of this powerful and often unpredictable natural phenomenon. The continued study of lightning, coupled with advancements in aircraft design and operational procedures, is essential for ensuring the safety of air travel in one of the world's most dynamic and awe-inspiring weather systems. The vibrant energy of a lightning strike, a fleeting spectacle of raw power, often leaves behind a far more persistent and destructive legacy: wildfires. While the immediate flash and thunder are dramatic, the true consequences of lightning-ignited fires are a surprisingly complex and scientifically investigated area. It's a story woven with dry brush, atmospheric conditions, and a careful look at how frequently and where these fires occur. The key isn't just that lightning can start a fire, but understanding why it's so effective at doing so. Lightning's immense energy, when it strikes the ground, doesn't simply burn the immediate point of impact. Instead, it creates a localized heat pulse. Think of it as a miniature explosion. This pulse dramatically elevates the temperature of the surrounding vegetation, far beyond what would be expected from a typical solar warming effect. The heat is incredibly intense, and the rapid temperature increase is enough to raise the moisture content in plants and soil to their flash point. The flash point is the temperature at which a substance ignites given sufficient oxygen. This is a crucial step. Most dry vegetation wouldn't ignite from the sun alone, but a lightning strike dramatically increases the chances. Several factors combine to amplify this effect. The type of vegetation plays a significant role. Grasslands and shrublands, particularly those with dry, fine fuels like grasses and small shrubs, are far more susceptible to lightning-ignited fires than forests with thicker, resinous trees. Resin helps insulate the wood and reduce the rate of heat transfer. Furthermore, the moisture content of the vegetation is a critical determinant. After periods of drought or high winds, vegetation is already stressed and drier, making it far more vulnerable. A lightning strike then acts as the critical ignition source. Statistical analysis of lightning-caused fires has revealed some fascinating patterns. Researchers use data from the National Lightning Detection Network, fire records, and weather observations to assess the relative contribution of lightning to wildfires across the United States, and now increasingly globally. While it's difficult to isolate lightning as the sole cause, many factors influence fire behavior. These studies consistently demonstrate that lightning is a significant contributor, often responsible for a substantial percentage of wildfires, particularly in certain regions. For instance, in areas with frequent lightning activity, like the western United States, lightning-caused fires account for approximately 20–30% of all wildfires. However, this percentage can fluctuate considerably depending on the year, the region, and the prevailing weather conditions. Beyond simply quantifying the number of lightning-caused fires, researchers are moving towards predictive modeling, attempting to forecast where these fires are most likely to occur. These models aren't just based on the presence of lightning. They incorporate a complex interplay of variables. One critical element is topographic data. Steep slopes and canyons can funnel wind, rapidly spreading fire flames across large areas. Models also factor in fuel load, the amount of combustible material available, which is itself influenced by factors like vegetation type, density, and past fire history. Another key component is weather data, including wind speed and direction, humidity and temperature. Strong winds accelerate fire spread, while low humidity increases the rate of evaporation, further drying out the fuel. Precipitation, conversely, dampens the effects of lightning and significantly reduces the risk of fire. These models aren't perfect, of course. Wildfires are inherently chaotic events, influenced by countless small variables that are impossible to predict with absolute certainty. However, advancements in computing power and data availability are steadily improving the accuracy of these models. Scientists are increasingly utilizing machine learning algorithms to identify patterns in historical fire data and predict future fire behavior. These algorithms can analyze vast amounts of information, including lightning strike locations, weather data, fuel maps, and topographic data to generate probabilistic fire danger maps. These maps don't tell us exactly where a fire will start, but they can highlight areas of elevated risk, allowing land managers to take preventative measures, such as targeted vegetation removal or strategic placement of fire breaks. Furthermore, researchers are exploring the use of satellite-based remote sensing to monitor fuel moisture content and vegetation health, providing real-time data that can be incorporated into predictive models. LiDAR, light detection and ranging technology, for example, can be used to create detailed 3D maps of vegetation, allowing scientists to assess fuel loads with unprecedented accuracy. The study of lightning-induced fires is an ongoing endeavor, driven by the need to better understand and mitigate this persistent threat. It's a reminder that even a seemingly brief and spectacular event like a lightning strike can have a lasting impact on our planet's ecosystems. Continued research and improved modeling capabilities are crucial to safeguarding communities and natural resources from the devastating consequences of these fires. The science behind it is about more than just understanding a single event. It's about managing the complex interactions between lightning, vegetation, and the atmosphere. The rumble of thunder, a sound so familiar, often carries with it a sobering thought: the potential for lightning to strike. While lightning's dramatic displays are captivating, understanding the actual risk it poses to human life is a complex and fascinating endeavor. Determining precise mortality rates from lightning strikes is surprisingly difficult, a challenge shaped by historical record-keeping, varying methodologies for investigation, and the often chaotic circumstances surrounding these events. Early accounts relied heavily on anecdotal evidence and local reports, offering a fragmented picture of a phenomenon that was frequently misunderstood and feared. For instance, in the late 18th and early 19th centuries, particularly in Europe and North America, lightning was frequently attributed to divine retribution, leading to heightened anxieties and, unsurprisingly, embellished narratives of victims. Documenting deaths directly caused by lightning was often secondary to attributing the event to other causes, like accidental falls or drownings, particularly when the immediate effects of a strike were devastating. Despite these difficulties, researchers have painstakingly built up a statistical basis for understanding lightning's lethality. Examining historical records reveals a startlingly low overall mortality rate from lightning strikes. Globally, estimates suggest that there are typically between 20 and 25 lightning strike fatalities per year. This figure represents a remarkable testament to both natural defenses. Our bodies are not particularly susceptible to electrical current, and advancements in safety practices. The vast majority of fatalities occur in regions with high lightning activity and relatively low population density, often in rural areas of the United States, Australia, and parts of South America. These regions, characterized by frequent thunderstorms and sparse infrastructure, present the highest risk. Looking at the United States, for example, accounts show that approximately 20 to 30 people die from lightning strikes annually, though this number fluctuates depending on weather patterns and public awareness campaigns. However, this global average obscures significant regional variations. The United States, due to its geographic location and frequent thunderstorm activity, accounts for a disproportionately large share of these deaths. Florida, in particular, has historically been the state with the highest number of lightning fatalities, largely because it is located within the cone, of a very common and intense thunderstorm formation known as the supercell. These supercells generate incredibly powerful and prolonged lightning, increasing the probability of a strike. Other states with high fatality rates include Texas, Oklahoma, and Kansas, all of which experience frequent, severe thunderstorms. Conversely, in many parts of the world, particularly Europe, Japan, and parts of South America, lightning fatalities are comparatively rare. This difference is influenced by several factors, including the frequency of thunderstorms, the population density of at-risk areas, and the availability of effective warning systems. Risk assessment for lightning strikes is a complex process that goes far beyond simply knowing the frequency of thunderstorms. It incorporates a multitude of variables. One key element is what's known as the strike probability. This isn't just about the chance of a thunderstorm forming. It's about the likelihood that lightning will actually strike a specific location, taking into account factors like elevation, ground conductivity, and even the surrounding vegetation. For instance, open, grassy areas, particularly those with high ground conductivity, meaning the ground is good at conducting electricity, tend to be more dangerous than forested areas, which can dissipate the electrical current. Similarly, being near tall objects like poles or towers can increase the risk. Another critical component of risk assessment is human behavior. People are significantly more likely to be struck by lightning while engaged in outdoor activities, especially those that take them into open spaces or put them in contact with conductive materials. Swimming, boating, fishing, hiking, and camping are all activities that elevate the risk. Furthermore, the effectiveness of lightning warning systems plays a crucial role. In regions with reliable and timely warnings, the number of fatalities can be significantly reduced as people are able to take shelter before a strike. These warnings often utilize a network of ground-based sensors that detect the electrical activity in the air, coupled with sophisticated weather models that predict the development of thunderstorms. Research continues to refine our understanding of lightning's impact, utilizing increasingly advanced technology. Scientists are using data from lightning detection networks, combined with detailed meteorological information, to build more accurate models of lightning behavior and to assess the risks associated with specific locations. These models aren't perfect, of course. Lightning is a chaotic phenomenon, and predicting its exact path is inherently difficult. However, these models are becoming increasingly valuable tools for emergency management agencies and for educating the public about lightning safety. Ultimately, while the raw power of a lightning strike remains a force of nature to be respected, the combination of statistical analysis, technological advancements, and a heightened awareness of risk is consistently reducing the number of lives lost to this spectacular, yet potentially deadly, natural event. The air crackles with a silent energy, a potential waiting to be unleashed. When lightning flashes across the sky, it's not just a blinding white, it's a surprisingly complex display of color. This phenomenon, far from being a simple optical illusion, reveals fascinating principles of light and the atmosphere itself. The color we perceive isn't the light produced by the lightning strike, but rather a result of how that light interacts with the air as it races toward the ground. The key to understanding this dance of color lies in something called Rayleigh scattering. Rayleigh scattering describes the preferential scattering of electromagnetic radiation, like sunlight or, in this case, lightning's energy, by particles of a much smaller wavelength. In the atmosphere, these tiny particles are primarily nitrogen and oxygen molecules. Now, consider that visible light is composed of a spectrum of colors, each with a different wavelength. Blue and violet light have the shortest wavelengths, while red and orange have the longest. Because blue and violet light are scattered more effectively by these air molecules, they are scattered in all directions. This is why the sky appears blue. It's the blue light, bounced around by the atmosphere, that reaches our eyes. During a lightning strike, an enormous amount of energy is released in a minuscule fraction of a second. This energy rapidly heats the air along the path of the lightning channel to incredibly high temperatures, hotter than the surface of the sun. This superheated air expands explosively, creating a channel of intensely hot plasma. It's this extremely hot plasma that's responsible for generating the light we see. However, it's not just blue light being produced. The intense heat causes all colors of the spectrum to be emitted. But again, the shorter wavelengths, blue and violet, dominate. But it gets even more interesting. Alongside Rayleigh scattering, another process contributes to the colors we observe: Raman scattering. Raman scattering is a vibrational phenomenon. When photons, particles of light, interact with molecules, they can cause the molecules to vibrate. This vibration changes the energy of the photon, resulting in the emission of photons with a different wavelength than the original photon. It's a sort of fingerprint of the molecule itself. In the case of lightning, the superheated air molecules, nitrogen, oxygen, and other trace elements, experience these vibrational shifts. This Raman scattering generates light at wavelengths slightly shifted from the initial emission spectrum, adding further complexity to the observed colors. This isn't just a simple scattering effect. It's a fundamental change in the light's energy state due to molecular interaction. The observed colors of lightning aren't solely determined by Rayleigh and Raman scattering, though. The emission spectra of the plasma itself play a crucial role. The specific composition of the plasma, the types and amounts of elements present, influence the wavelengths of light emitted. For example, the presence of sodium can lead to a characteristic yellow or orange hue in some lightning discharges. Similarly, magnesium can produce a brilliant green color. The blue color we predominantly see in most lightning flashes isn't simply the most intensely scattered color. It's the result of the combined effects of Rayleigh scattering from the cooler, surrounding air, plus the dominant emission from the plasma itself, all working together. The air molecules are scattering the light before the plasma's light has a chance to fully dominate the observed spectrum. Furthermore, the path length of the lightning channel matters. A longer channel means more air molecules are interacting with the plasma's light, and therefore, a greater contribution from the plasma's emission spectrum to the overall observed color. A shorter, more concentrated channel will predominantly display the plasma's emissions. Observing lightning colors is also affected by atmospheric conditions. Humidity, for instance, can influence the scattering process, subtly shifting the observed spectrum. Dust and other particulate matter in the air can also scatter light, creating additional distortions and variations in the colors. Scientists use instruments called spectrometers to analyze the light emitted by lightning. These instruments precisely measure the intensity of light at different wavelengths, providing a detailed map of the color composition of a lightning strike. This information allows researchers to better understand the physical processes occurring within the plasma channel and to model the behavior of lightning itself. The next time you witness a brilliant lightning flash, remember that you're seeing more than just a burst of white light. You're witnessing a stunning demonstration of physics, a complex interplay of scattering, emission, and molecular vibrations, all contributing to one of nature's most spectacular displays. It's a reminder that even the most dramatic events in the sky are governed by the elegant and intricate laws of the universe. The world hums with invisible connections. We carry them in our pockets, see them flickering across our televisions, and rely on them for everything from ordering a pizza to coordinating international aid. These connections, built on the principles of electromagnetic radiation, travel vast distances, carrying voices, images, and data across oceans and continents. But these sophisticated systems, our radio networks, television broadcasts, and most crucially, our satellites, are incredibly vulnerable to a force of nature that's both beautiful and immensely powerful: lightning. While the immediate danger of a direct strike is a serious concern, the impact of lightning on global communication is far-reaching and often less obvious than a downed power line. It's a story of invisible interference, of shattered signals, and the urgent need for systems to anticipate and mitigate these disruptions. Lightning's electrical discharge isn't simply a flash of light. It's a colossal surge of electromagnetic energy. When a lightning bolt reaches the ground, it releases an enormous amount of energy, far more than a typical electrical outlet could ever handle. This energy propagates outwards in all directions, creating a complex and rapidly changing electromagnetic field. This field interacts with the natural electromagnetic waves already in use for communication. Radio waves, for example, are a form of electromagnetic radiation, and just as light waves can bend around obstacles, so too can lightning's electromagnetic waves. The key here is understanding how these waves interact. Radio waves, used for everything from shortwave radio broadcasts to cellular phone communication, travel in straight lines. However, a lightning discharge creates a localized, rapidly fluctuating magnetic field. This field induces currents, essentially tiny electrical flows, within conductive materials, including the antennas and cables used in radio transmission. These induced currents corrupt the original signal, creating noise and distortions. Imagine trying to listen to a clear radio station when someone is repeatedly turning a dial. That's a simplified analogy for what happens when lightning introduces interference. The effects are particularly pronounced at higher frequencies. Satellite communication relies on precisely modulated microwave signals to transmit data between ground stations and orbiting satellites. These satellites are incredibly sensitive, operating within narrow bands of the electromagnetic spectrum. A lightning strike near a satellite, or even a significant distance away, can generate electromagnetic pulses, EMPs, that severely disrupt these signals. These pulses, characterized by their rapid rise and fall in energy, are capable of overwhelming the satellite's receiver, causing temporary or even permanent loss of communication. The impact isn't limited to satellites. High-frequency radio communication, used by aviation and maritime services, is also susceptible. Radar systems, utilized for weather forecasting and air traffic control, are particularly vulnerable. A strong lightning strike can overwhelm the radar receiver, producing false readings and potentially disrupting vital operational procedures. Think of the complex calculations that go into modern air traffic control. A momentary disruption caused by lightning could have serious consequences. Furthermore, the disruption isn't always immediate or obvious. While a direct strike to a communication facility would undoubtedly cause a noticeable outage, the more insidious effects can occur gradually. Repeated, smaller lightning-induced currents can subtly degrade signal quality over time. These cumulative effects, difficult to pinpoint, can lead to unreliable communication links and necessitate frequent system recalibration. Scientists and engineers have been working for decades to understand and mitigate these effects. One approach involves shielding communication equipment with specialized materials designed to block electromagnetic interference. Grounding systems, meticulously designed to direct lightning currents safely to the Earth, are crucial for protecting infrastructure. However, the sheer scale of lightning events makes complete protection impossible. More recently, research has focused on developing lightning-tolerant communication systems that can continue to operate, albeit with reduced capacity, during and immediately after a lightning storm. These systems often incorporate redundancy, allowing for automatic switching to backup channels, and sophisticated algorithms that can filter out noise and detect and correct errors in the data stream. The study of lightning's impact on communication also plays a vital role in space weather forecasting. Space weather, encompassing phenomena like solar flares and coronal mass ejections, can significantly influence the Earth's magnetic field and, consequently, the frequency and intensity of lightning strikes. Monitoring these patterns can help predict potential disruptions to communication systems and allow for proactive measures to be taken. It's a continuous balancing act, harnessing the power of electromagnetic waves for global connection, while acknowledging and addressing the natural force that threatens to unravel them. The ongoing research and development in this area are testament to our ingenuity and our reliance on these invisible networks, and a powerful reminder of the forces that shape our world. Understanding these vulnerabilities isn't just about technological resilience. It's about appreciating the delicate interplay between humanity and the raw power of nature. The vastness of the night sky has always held a particular fascination for humans, a primal urge to look up and ponder the mysteries hidden amongst the stars. But sometimes, those mysteries aren't found solely in distant planets or swirling galaxies. Occasionally, the most spectacular light shows come from directly above us, shimmering curtains of green, pink, and violet dancing across the polar skies. These are the auroras, more formally known as the aurora borealis in the northern hemisphere and the aurora australis in the southern. And the surprising truth is that these breathtaking displays, seemingly so distant and ethereal, are intricately linked to the very phenomenon that causes lightning to flash across our terrestrial landscapes. The relationship began to unravel in the mid-20th century, largely through the pioneering work of physicists like Lewis Allen at the Massachusetts Institute of Technology. Allen's groundbreaking research centered on the idea of impressed current, a concept that fundamentally shifted our understanding of how auroras form. It wasn't enough to simply believe that charged particles from the sun were passively interacting with the Earth's magnetic field. Allen proposed a much more active process. He theorized that lightning itself played a crucial, initiating role in creating the conditions necessary for auroral formation. The sun, you see, is a constant source of energy, relentlessly showering the Earth with a stream of charged particles, primarily electrons, known as the solar wind. This wind flows outwards, largely unimpeded, until it encounters the Earth's magnetic field. The magnetic field, shaped like a giant teardrop around our planet, acts as a shield, deflecting most of this solar wind. However, at the poles, where the magnetic field lines run almost vertically into the atmosphere, the solar wind manages to penetrate, creating a zone known as the magnetosphere. Now let's consider lightning. A typical lightning strike isn't just a random discharge of electricity. It's a complex process of charge separation, where areas within a cloud accumulate opposite electrical charges. These charges build up until the air, the insulating material, can no longer hold them. Then, a sudden, dramatic release occurs, a stepped leader, a channel of ionized air, reaching downwards towards the ground. This is followed by the return stroke, the brilliant flash we see as the current rushes back up to the cloud. But the return stroke isn't just an isolated event. The energy released is immense, far greater than that of a typical thundercloud. What Allen discovered, and what subsequent research has confirmed, is that these gigantic return strokes can, under the right circumstances, actually create the initial pathways for auroral light. The stepped leader, instead of always aiming directly for the ground, can be influenced by the influx of energy from a strong return stroke. If a particularly powerful return stroke occurs near the top of a thunderstorm, it can inject a huge pulse of energy into the atmosphere. This pulse, carrying a significant amount of charged particles, can create a temporary, highly conductive channel, a magnetic field-aligned current in the ionosphere, the upper atmosphere where the auroras predominantly appear. This newly formed channel acts as a conduit, allowing further charged particles from the solar wind to readily enter the atmosphere. These incoming particles then collide with atmospheric gases, primarily oxygen and nitrogen, exciting their atoms. When these excited atoms return to their normal state, They release energy in the form of light, producing the characteristic colors of the aurora. Green light, the most common color, is produced by oxygen at lower altitudes, while red light, a rarer sight, comes from oxygen at higher altitudes. Nitrogen contributes to the pink and violet hues. The connection isn't always straightforward, of course. The intensity and appearance of the aurora depend on several factors, including the strength of the solar wind, the geometry of the Earth's magnetic field, and the density of ions in the ionosphere. A particularly intense coronal mass ejection, CME, a massive burst of solar material, can dramatically amplify the effect, leading to spectacular displays of aurora visible at lower latitudes than usual. Scientists can even monitor these CMEs and predict the potential arrival of intense auroral activity. Moreover, the research has revealed that lightning in polar regions, particularly during geomagnetic storms, plays a more consistent and fundamental role. The continuous pulses of energy from lightning repeatedly kickstarts the process, maintaining the conductive channels necessary for the sustained formation of the aurora. It's a feedback loop. Lightning creates the conditions, and the aurora, in turn, reinforces those conditions. Looking at the aurora isn't just about admiring a beautiful light show. It's a tangible demonstration of the profound interplay between the sun, the earth, and its atmosphere, revealing the surprising ways that seemingly distant events can have dramatic effects right here on our planet. The next time you gaze up at the dancing lights of the aurora, remember the lightning flashes that helped bring them to life, a powerful reminder of the universe's hidden connections. The air around a lightning strike isn't simply a flash of light and a tremendous noise. It's a chemical reaction zone, a fleeting but incredibly powerful laboratory happening high above our heads. While we often think of lightning's immediate effects, the damage to structures, the frightening spectacle, its influence on the very composition of the atmosphere is a more subtle and arguably more significant story. Lightning, particularly when it occurs in certain types of storms, acts as a catalyst, triggering processes that transform atmospheric gases into substances with far-reaching consequences. The most well-documented of these transformations revolves around nitrogen oxides, specifically nitrogen dioxide, NO2, and nitric acid, HNO3. These compounds aren't naturally abundant in the upper atmosphere. They're largely produced through photochemical reactions, those driven by sunlight in the troposphere, the lowest layer of the atmosphere where we live. However, the energy released during a lightning strike dramatically accelerates these reactions, creating concentrations of nitrogen oxides far exceeding what would normally be found. Consider the nitrogen in the air. It's mostly in the form of nitrogen gas, N2, a very stable molecule. But nitrogen can also exist as nitrogen oxides, which are much more reactive. The process begins with the dissociation of nitrogen molecules themselves. When a lightning channel forms, it generates intense electric fields. These fields can cause nitrogen molecules to break apart, forming nitrogen atoms. These free nitrogen atoms are highly reactive and immediately combine with oxygen molecules already present in the air. The initial product of this combination is nitrogen dioxide. This compound is then subject to further reactions, driven by the presence of water vapor and ultraviolet radiation from the sun. Water vapor acts as a crucial ingredient, providing the necessary hydrogen atoms to form nitric acid. The high energy from the lightning strike provides the necessary activation energy to kickstart these complex chemical cycles. The quantity of nitrogen oxides generated during a thunderstorm is astonishing. A single lightning flash can produce several tons of nitrogen oxides. That's enough to significantly alter the chemistry of the upper atmosphere for a considerable period. But the impact doesn't stop with nitrogen oxides. These newly formed compounds have a particularly concerning effect on ozone. Ozone, O3, is a vital shield in the stratosphere, absorbing harmful ultraviolet radiation from the sun. Nitrogen oxides, especially NO2, are ozone destroyers. They participate in a chain of reactions that break down ozone molecules. The process isn't a simple one. It involves a series of complex steps, but fundamentally, the nitrogen oxides effectively remove ozone from the stratosphere. The degree of ozone depletion caused by lightning is still being actively researched, and while it's a smaller factor than human-produced ozone-depleting chemicals like chlorofluorocarbons, CFCs, it's nonetheless a demonstrable effect. The thunderstorms that produce these elevated levels of nitrogen oxides are often associated with mesoscale convective systems, large, organized storm complexes that can span hundreds of kilometers. These storms, characterized by strong updrafts and downdrafts, can lift air to very high altitudes, transporting nitrogen oxides produced closer to the surface into the upper atmosphere. The sheer scale of these storms amplifies the chemical effects. Furthermore, the distribution of nitrogen oxides isn't uniform. The lightning channels themselves create localized zones of intense chemical activity. The air immediately surrounding a strike is subjected to the highest concentrations of these compounds. Studies have shown that these areas can act as chemical hotspots, significantly impacting the surrounding atmospheric chemistry. The intensity of the lightning itself directly correlates with the magnitude of the chemical changes observed in the immediate vicinity. The long-term consequences of lightning-induced nitrogen oxide formation are still being investigated. While the immediate effects are relatively well understood, the fate of these nitrogen oxides in the atmosphere is complex. They can be transported downwards, contributing to air pollution in the lower atmosphere, particularly in regions with frequent thunderstorms. They can also undergo reactions that eventually lead to the formation of other compounds, further altering atmospheric chemistry. Research continues to focus on understanding the atmospheric lifetime of these nitrogen oxides and their overall impact on global atmospheric processes. It's important to remember that lightning's influence on atmospheric chemistry is interwoven with a vast network of natural processes. It doesn't operate in isolation. It interacts with solar radiation, atmospheric circulation patterns, and the existing composition of the air. The magnitude of the effect depends on many factors, including the type of storm, the intensity of the lightning, and the prevailing atmospheric conditions. Despite its seemingly dramatic nature, lightning's contribution to atmospheric chemistry is a testament to the intricate and interconnected nature of our planet's systems. Understanding this connection allows us to appreciate the full extent of lightning's impact, extending far beyond its visible flash and thunderous roar. It's a reminder that even seemingly destructive phenomena can play a role in shaping the very air we breathe. The sky isn't just a beautiful expanse of blue and white. It's a swirling, dynamic place, a giant laboratory where electrical charges dance and build until they suddenly, spectacularly, release themselves as lightning. But not all lightning looks the same. It's far more complicated than a single flash, and understanding the different types reveals a much richer picture of how storms operate and the incredible forces at play within them. We'll explore the most common types: cloud to ground, intra-cloud, cloud to cloud, and a truly mysterious phenomenon called ball lightning. Let's begin with the most familiar kind, cloud-to-ground lightning. This is the type we often think of when we picture a thunderstorm. It happens when a significant buildup of negative charge concentrates within a thunderstorm cloud, typically the lower regions, and positive charge accumulates in the surrounding air. This difference in electrical potential becomes so strong that the air, which is normally an excellent insulator, breaks down. A stepped leader, a faint, jagged channel of negative charge, begins to descend from the cloud, seeking the ground. As it gets closer, it triggers positive charge in the ground below trees, buildings, even the earth itself, to rush upwards in a connecting streamer. When these two channels meet, a powerful return stroke of positive charge surges back up to the cloud, creating the brilliant flash we see. This return stroke is actually the brightest part of the lightning discharge, as it carries the majority of the energy. Often, a single lightning flash isn't just one return stroke, it's a series of them, as the negative charge continues to propagate along the established channel. The sound we hear, the thunder, is caused by the rapid heating and expansion of air along this channel. It's essentially a sonic boom created by the sudden movement of air. The longer the delay between the flash and the thunder, the farther away the lightning strike is. Now consider intra-cloud lightning. This type occurs within a single thunderstorm cloud, rather than between clouds. It's often far more frequent than cloud-to-ground lightning and can take many forms. It can be caused by the complex interactions between positive and negative charge within the cloud itself. Think of it like a giant, internal electrical storm, with charge building up in different pockets and then discharging within those pockets. These discharges can be particularly intense and unpredictable, appearing as multiple, rapidly flickering flashes within the cloud. They often occur in complex patterns, sometimes resembling curtains or sheets of light. These flashes often produce a distinct, high-pitched crackle sound, separate from the rumble of thunder. Cloud-to-cloud lightning is another prevalent type, and it's a fascinating example of how storms can connect. It happens when a thunderstorm develops a strong electric field between two or more clouds. The same principles of charge separation apply, one cloud accumulating a positive charge, the other a negative charge. But instead of discharging directly to the ground, the electricity jumps across the gap between the clouds. These discharges can be incredibly energetic, and they're often seen as a continuous, undulating glow rather than a sudden flash. They frequently appear as a curtain of light stretching between the cloud tops and can be seen from very long distances. But perhaps the most elusive and least understood type of lightning is ball lightning. For centuries, people have reported seeing glowing, spherical objects associated with thunderstorms. These balls can range in size from a few centimeters to over a meter in diameter, and typically last for a few seconds before disappearing. Their appearance is incredibly variable, and they can be luminous, translucent, or even appear as dark spheres. Scientists have proposed several theories about their formation, but none have been definitively proven. One popular theory suggests that ball lightning is created when nitrogen oxides, produced during lightning discharges, react with oxygen in the air, forming a glowing plasma, a superheated, ionized gas. Another theory proposes that it's created by the interaction of lightning with dust particles in the air. However, the precise mechanisms are still being investigated, and the fact that ball lightning is so rare and unpredictable makes it a challenging phenomenon to study. The color of ball lightning has also been a subject of fascination. It's been observed in a range of colors, including white, yellow, orange, blue, and even violet. This variation is likely due to the different temperatures and densities within the plasma. The energy released during the formation and dissipation of ball lightning is immense, and understanding this fleeting phenomenon remains a significant puzzle for atmospheric scientists. Despite the numerous observations, the exact physics behind ball lightning is still shrouded in mystery. It's a reminder that even in the familiar world of thunderstorms, there are still remarkable secrets waiting to be uncovered. The most immediate and dramatic consequence of a lightning strike isn't the flash itself, but the intense electric field it creates. When a massive charge separation occurs within a thundercloud, a process involving ice crystals, water droplets, and strong updrafts, a tremendous imbalance of electrical potential develops. This potential isn't uniform. It's concentrated in a region around the point where the lightning bolt actually connects with the ground or another part of the cloud. Understanding the strength of this electric field is crucial not only for appreciating the power of lightning, but also for assessing the potential dangers it presents. It's like a giant, invisible hand, exerting a force that can affect anything in its path. Measuring the electric field strength is a fascinating and surprisingly delicate undertaking. The basic principle is quite straightforward. An electric field exerts a force on any charged object. Scientists use instruments called field mills to detect and quantify this force. These aren't your everyday voltmeters. They're specialized devices designed to sense extremely weak electric fields. A field mill typically consists of a small, lightweight capacitor, a device that stores electrical energy, with extremely thin, conductive plates. These plates are suspended, often supported by a delicate framework, and are incredibly sensitive to even the tiniest changes in electric field strength. As a lightning strike occurs, the capacitor, being near the discharge point, experiences a surge of current. The tiny movement of charge within the capacitor plates generates a measurable voltage change, which is then translated into a reading on the field mill's display. The unit of measurement for electric field strength is newtons per coulomb, NC. This tells us how much force in newtons a single coulomb of charge would experience in that particular location. A higher NC value indicates a stronger electric field. The intensity of the electric field doesn't remain constant immediately after a lightning strike. It rapidly decreases with distance from the strike point, following an inverse square law. This means that the electric field strength drops off dramatically as you move further away. It's like the sound of a shout fading into silence. However, the field isn't simply zero beyond a certain radius. It still exists, albeit at a much weaker level. The shape of this decline is influenced by several factors, including the conductivity of the ground and the geometry of the lightning channel itself. Dry ground, for example, provides a more efficient path for the electric field to dissipate, leading to a faster decline. Moist ground, on the other hand, slows down the dissipation, resulting in a longer-lasting, albeit weaker, electric field. The potential hazards associated with this electric field are significant. While most people don't experience direct harm from the field itself, the sheer magnitude of the current flowing through the air creates a zone of danger. Animals, especially smaller ones like birds or rodents, are particularly vulnerable. The strong electric field can induce a current through their bodies, leading to cardiac arrest, muscle spasms, or nervous system damage. The effects are often immediate and devastating. Larger animals like horses or cattle might experience involuntary muscle contractions, potentially leading to falls or trampling. Beyond animal life, the electric field can also induce currents in metallic objects, fences, power lines, even metal tools or vehicles within its vicinity. This is known as inductive coupling. The strength of the induced current depends on the conductivity of the object and the strength of the electric field. A metal fence, for example, could become a conduit for the lightning's current, potentially delivering a dangerous shock to anyone attempting to pass through it. Similarly, a car parked near a lightning strike could experience a surge of current through its electrical system, damaging the engine or electronics. Furthermore, the electric field can affect the ionization of air molecules around the strike point. The intense current creates a path of ionized air molecules stripped of their electrons, extending outwards. This ionized air is highly conductive, further enhancing the electric field and contributing to the propagation of the electrical discharge. This process is thought to play a role in the steps, or pulses, often observed in lightning flashes, where the discharge seems to jump back and forth along the channel. Researchers utilize sophisticated ground-penetrating radar and electromagnetic surveys to map the extent of the electric field after a lightning strike. These techniques help identify areas where the electric field is particularly strong and where potential hazards might exist. They can also provide valuable insights into the complex electromagnetic interactions that occur during a lightning discharge, revealing details about the lightning channel's geometry and the mechanisms driving the electrical breakdown. The study of lightning's electric field is not just about understanding a natural phenomenon. It has practical applications. For example, data collected from lightning strike monitoring systems can be used to improve the accuracy of lightning forecasting models, allowing for more timely warnings and reducing the risk of damage to infrastructure and property. Advances in sensor technology are enabling the development of wearable devices that could potentially detect and alert individuals to the presence of a strong electric field, providing a crucial early warning system. The continuing investigation of these fields reveals a complex interplay of physics and electromagnetism, a reminder of the immense power lurking within storms. The sudden, brilliant flash of a lightning strike doesn't just illuminate the sky. It carries with it an immense, invisible force, a powerful electrical current that can dramatically alter the materials surrounding it. Buildings, designed for centuries to come, are surprisingly vulnerable to these fleeting but potent assaults. The immediate heat generated by a lightning strike, far hotter than the surface of the sun, isn't the only concern. The electrical discharge itself leaves lasting marks on a building's structure and its protective layers. Let's explore how lightning's energy manifests as damage to the materials we rely on for safety and longevity. The most readily observable consequence of a lightning strike on a building is often corrosion. While corrosion is a gradual process involving oxidation, the reaction of a material with oxygen, lightning, dramatically accelerates this reaction. A single strike can deliver enough electrical energy to trigger a massive surge of electrochemical activity within metals. Iron, a common component in building materials like steel reinforcement in concrete, is particularly susceptible. The intense current causes metal atoms to lose electrons, creating positively charged ions that quickly react with oxygen and water vapor in the air. This generates rust, but not the slow, gradual rust we typically see. A lightning strike produces a thick, spongy, and intensely colored layer of corrosion, often referred to as fire scale, that can completely obliterate the original metal surface in a matter of hours or days. Copper, used in wiring and roofing, reacts similarly, forming a greenish patina characterized by copper carbonates and sulfates. Aluminum, while generally more resistant, can still experience significant pitting corrosion due to the electrolytic action of the discharge. The scale formed isn't just unsightly, it compromises the material's structural integrity, weakening the metal and ultimately leading to further deterioration. Beyond the surface corrosion, lightning can profoundly disrupt the insulation properties of buildings. Insulation, whether it's fiberglass in walls, foam boards in attics, or mineral wool used for thermal and acoustic control, plays a vital role in maintaining comfortable temperatures and minimizing energy consumption. The electrical discharge induces a cascading series of physical and chemical changes within these materials. High temperatures cause rapid thermal expansion and contraction, leading to microcracks and bond failures. Furthermore, the intense electromagnetic fields generated by the lightning can break down the molecular structure of the insulation itself. For example, in fiberglass insulation, the filaments can become detached and lose their ability to effectively trap heat. In foam insulation, the cellular structure can collapse, reducing its density and insulating capacity. This degradation isn't limited to traditional insulation types. Even modern materials like spray foam can suffer damage, leading to significant energy loss and increased heating-cooling costs. The extent of the damage depends on the type of insulation, its thickness, and the intensity of the strike. The effects aren't limited to materials that are directly hit by the lightning. Surges of electricity can travel through conductive pathways within a building's electrical system, inducing damage in seemingly unaffected areas. Wiring can overheat and burn, insulation can melt, and even electronic components can be destroyed. The electrical field generated by the strike can also create conductive pathways through building materials like concrete and brick, allowing current to flow through the structure. This can lead to significant damage to interior walls, floors, and ceilings, often manifesting as discoloration, cracking, or even localized collapse. The strength of this induced current depends on the building's electrical system, its grounding, and the proximity of the lightning strike. Buildings with poor grounding are particularly vulnerable, as the electricity has no safe path to dissipate, increasing the risk of widespread damage. Structural damage from lightning is often complex and can vary greatly depending on the building's construction, the location of the strike, and the amount of energy discharged. While a direct hit to a load-bearing wall may cause immediate collapse, more subtle damage can occur through induced stresses within the structure. The rapid heating and cooling cycles associated with a lightning strike can cause expansion and contraction, creating internal stresses that weaken the materials over time. Concrete, for example, can develop hairline cracks, especially if it's subjected to repeated thermal cycling. Similarly, wood can become weakened due to the breakdown of cellulose fibers. The presence of fire scale, the intensely corroded surface layer, adds to the structural vulnerability as it compromises the integrity of the underlying material. Furthermore, the forces generated by a lightning strike can cause vibrations throughout a building's structure, particularly in tall buildings or those with flexible designs. These vibrations can exacerbate existing weaknesses and contribute to long-term damage. Assessing the structural impact of lightning damage requires specialized engineering analysis, considering factors like material properties, building geometry, and the magnitude of the electrical discharge. Insurance companies often employ forensic engineers to evaluate lightning damage claims, meticulously documenting the extent of the damage and determining the cause. Ultimately, protecting buildings from lightning's destructive effects involves a combination of preventative measures, including proper grounding, surge protection devices, and careful building design, alongside robust building codes and regulations. The sky pulsed with an almost visible energy, a consequence of the immense electrical charges building within storm clouds. But what exactly was happening beneath that dramatic display of light and sound? Scientists have long suspected a deeper, more intricate connection between lightning and the Earth itself, a connection primarily explored through the fascinating field of geomagnetic studies. It wasn't simply about observing lightning. It was about measuring how these colossal discharges interacted with the planet's magnetic field, and whether those interactions revealed something truly remarkable. Early investigations focused on identifying anomalous magnetic readings around lightning strike locations. Researchers noticed, consistently, that the magnetic field would experience a sharp, temporary disturbance immediately following a strike, often lasting for several seconds to minutes. These weren't just fleeting blips. The changes were measurable, quantifiable, and repeatable across numerous observations. The key was recognizing that lightning isn't just a random event discharging electricity. It's a process that profoundly perturbs the Earth's magnetic field. The initial attempts to understand these magnetic anomalies centered on proposing that the enormous electrical currents flowing during a lightning strike directly induced a corresponding magnetic field. It's a principle rooted in electromagnetism. A moving electric charge generates a magnetic field, and a large current is, by definition, a massive flow of charge. However, the magnitude of the disturbance observed often exceeded what could be predicted solely by this simple model. The measured magnetic changes were significantly stronger than expected, hinting that something more complex was at play. This sparked a wave of research into the possibilities of plasma formation. Lightning, as we've discussed, creates a highly ionized channel, a stream of plasma, as the electric field forces electrons out of the air molecules. This plasma isn't just a byproduct. It's a central component of the lightning discharge itself. The prevailing theory, developed and refined over decades, suggested that this lightning-generated plasma interacted with the Earth's magnetic field in a truly transformative way. The Earth's magnetic field, created by the movement of molten iron in its core, acts as a protective shield, deflecting much of the harmful solar wind, a constant stream of charged particles from the sun. However, during a lightning strike, the plasma channel momentarily disrupts this protective barrier. The intense, localized magnetic field created by the lightning pulse interacts with the surrounding magnetic field lines, bending and twisting them. This interaction doesn't just cause a momentary magnetic disturbance. It appears to facilitate the transfer of energy and possibly even charged particles between the lightning channel and the surrounding geomagnetic environment. Researchers began to correlate lightning strike location with observed magnetic anomalies, particularly with what are known as magnetic anomalies. These anomalies are areas where the Earth's magnetic field strength deviates significantly from its normal value. Before the widespread observation of lightning-induced disturbances, many of these anomalies were considered geological curiosities, perhaps related to subsurface mineral deposits or variations in the Earth's crust. However, the timing of the anomalies began to align remarkably with lightning events, especially in regions with high lightning activity, such as the Florida Peninsula. Advanced instrumentation, including magnetometers, devices that precisely measure magnetic fields, became crucial in this investigation. Scientists started deploying networks of magnetometers strategically positioned in areas known for frequent lightning strikes. These networks allowed for real-time monitoring of magnetic fluctuations and, critically, for identifying patterns and correlations between lightning events and the resulting changes in the magnetic field. Some studies even pointed to a possible link between particularly intense lightning storms and the creation of transient magnetic anomalies, brief, temporary deviations from the baseline magnetic field strength. The research isn't without its complexities and ongoing debates. Determining the exact mechanisms by which lightning influences the geomagnetic field remains a significant challenge. It's clear that the interaction is complex, involving plasma physics, electromagnetic forces, and potentially even the transfer of energy and momentum between the lightning channel and the Earth's magnetic field. Some scientists propose that the lightning strike essentially scrapes or modulates the magnetic field lines, creating ripples and disturbances that propagate through the geomagnetic environment. Others explore the possibility of the plasma channel acting as a conduit, transporting magnetic energy over short distances. Furthermore, the study of lightning and geomagnetism isn't limited to Earth. Observations have been made on the Moon and other planets with atmospheres, though the mechanisms may differ due to variations in atmospheric composition and magnetic fields. The research continues, driven by the tantalizing prospect that lightning isn't merely a spectacular atmospheric phenomenon, but a fundamental process that actively shapes the Earth's magnetic field and contributes to the complex dynamics of our planet's environment. Ultimately, understanding this connection provides a deeper appreciation for the intricate relationships that exist within our world, a constant interplay between electricity, magnetism, and the very fabric of the planet we call home. The data collected from studying lightning and the geomagnetic field continues to refine our models and hopefully, one day, reveal the full extent of this fascinating, dynamic interaction. The sky wasn't just blue, not really. It was a vast, shimmering ocean of charged particles, constantly being sculpted by the sun's relentless energy. The sun, you see, is a giant nuclear furnace, blasting out streams of tiny particles, electrons, into space. These particles, accelerated to incredible speeds, interact with Earth's magnetic field, creating the solar wind. This constant bombardment of charged particles doesn't just flow around our planet. It's actually absorbed by the upper atmosphere, particularly in the mesosphere and ionosphere, which are layers of gas extending far above us. As these solar particles collide with atmospheric gases like oxygen and nitrogen, they become energized, stripping electrons away and creating a vast, ever-shifting reservoir of electrical charge. This newly created charge isn't evenly distributed. The electrical potential, that invisible force that makes static cling happen, is strongest in the ionosphere, a region where the solar wind is most intense. It's like a gigantic capacitor, a device that stores electrical energy, only instead of metal plates, it has a layered atmosphere acting as its dielectric. The ionosphere, therefore, holds an enormous amount of electrical potential, far greater than anything we could ever produce on the ground. But this potential is unstable. It's constantly fluctuating, responding to the solar wind's ebb and flow, and to disturbances in the Earth's magnetic field itself. Now let's talk about thunderstorms. Thunderstorms, magnificent displays of atmospheric electricity, aren't isolated events. They're actually crucial nodes within a global electrical circuit. Within a thunderstorm, immense electrical fields build up due to the rapid movement of ice crystals and supercooled water droplets. That is, water that's still liquid even though it's below freezing. These particles are violently jostled by the strong updrafts and downdrafts of the storm, causing them to accumulate charge. Typically, the upper portion of the cloud becomes positively charged, while the lower portion becomes negatively charged. This charge separation isn't random. It's driven by the complex interactions within the storm. The key to understanding this connection lies in the Earth's magnetic field. The magnetic field acts as a conductor, a pathway for electrical current. When a lightning strike occurs, the immense electrical potential difference between the negatively charged cloud base and the positively charged ground, or sometimes another cloud, overcomes the resistance of the air. A massive current, often measured in tens of thousands of amperes, flows from the cloud to the ground, creating a visible lightning channel. But the current doesn't just stop at the point of contact. It continues to flow along the ionized air channel, often extending for several kilometers. And crucially, this current doesn't just disappear into the ground. Instead, it's channeled by the Earth's magnetic field lines, essentially following the paths of least resistance. These magnetic field lines, constantly being shaped and distorted by the solar wind and other disturbances, act like highways for electrical current. Think of it like this. The lightning strike is like a powerful surge of water flowing into a river. That river, the Earth's magnetic field, then carries that water, the electrical current, to other parts of the planet. Research using sensitive electrical instruments has demonstrably shown that lightning strikes in one region can induce small electrical currents in distant areas, even thousands of kilometers away. This phenomenon is known as electroreception in some animals, like sharks, who can sense these subtle electrical fields. However, the connection is more than just a localized effect. The global electrical circuit is actively maintained by these lightning events. Furthermore, the flow of electricity isn't solely horizontal, following the magnetic field lines. The ionosphere itself acts as a conductor, facilitating the transfer of electrical energy across vast distances. Scientists have observed electrical signals traveling along the ionospheric currents, often hundreds or even thousands of kilometers. These signals are generated by lightning strikes, and they provide a tangible demonstration of the interconnectedness of the global electrical system. The magnitude of this global electrical circuit is truly staggering. Estimates suggest that the total electrical power discharged by lightning strikes around the world is equivalent to hundreds of terawatts. That's 1 trillion watts. This continuous transfer of energy, driven by solar activity and the dynamics of thunderstorms, significantly influences the electrical state of the ionosphere and contributes to the overall electrical balance of the planet. Scientists continue to study this complex system, employing sophisticated instruments to monitor electrical currents, magnetic field variations, and ionospheric conditions. These studies reveal that the global electrical circuit isn't just a theoretical concept. It's a real, measurable phenomenon that plays a critical role in the planet's electrical environment. The exchange of energy between the atmosphere and Earth, facilitated by lightning, is a constant, dynamic process, inextricably linked to the weather, the solar wind, and the very fabric of our planet's electrical system. It's a grand, awe-inspiring demonstration of the interconnectedness of nature. Ongoing research, including satellite observations and ground-based measurements, continues to refine our understanding of this global electrical circuit, revealing new insights into the intricate relationships between lightning, the ionosphere, and the wider solar system. It's a story still being written, a story of energy, charge, and the breathtaking power of the natural world. The sky wasn't just blue today, it was brimming with potential. Scientists had long known that lightning and severe weather, particularly thunderstorms, were deeply intertwined. But understanding how to predict this connection with greater accuracy was a challenge that kept meteorologists busy. The raw observation of a lightning strike was valuable, of course, but it was like noticing a single raindrop and trying to forecast a downpour. It lacked the bigger picture. The key was realizing lightning wasn't just a random event. It was often a leading indicator of a larger, more dangerous system already building in the atmosphere. Modern weather forecasting relies heavily on numerical weather prediction, or NWP. These models are essentially incredibly complex computer simulations that take into account countless factors: temperature, pressure, humidity, wind speed, and direction, to predict how the atmosphere will change over time. These models started with relatively simple equations, but they've evolved dramatically over the decades, incorporating ever-increasing levels of detail and sophistication. The accuracy of a forecast depends entirely on the quality of the initial conditions, the starting point of the simulation. This is where lightning data began to play a crucial, previously underutilized role. Traditionally, NWP models were primarily driven by observations from surface stations, those little boxes measuring temperature and rainfall, and from weather balloons that rose through the atmosphere, relaying temperature, humidity, and wind information. Satellites also provided valuable data, offering a broad view of cloud cover and atmospheric conditions. However, these traditional data sources weren't always perfect, and they didn't capture the very localized, rapidly changing conditions that often precede a significant thunderstorm. Lightning, with its intense electrical activity and accompanying atmospheric disturbances, offered a complementary source of information. As a thunderstorm develops, particularly a supercell thunderstorm, known for its rotating updraft and potential for hail and tornadoes, it creates highly organized electrical fields. These fields aren't uniform. They're concentrated in areas of strong instability, where warm, moist air is rising rapidly through cooler, drier air. The intensity and frequency of lightning strikes are directly related to the strength of this instability. Scientists began to develop systems to detect lightning in real time. These systems, often using networks of ground-based lightning detection sensors, could pinpoint the location and characteristics of each strike, its altitude, its intensity, and its timing. These data were then fed into NWP models. It's not simply about knowing where lightning occurred, but how often and where it was happening in relation to the existing weather patterns. For instance, a cluster of intense lightning flashes in a particular area indicated a strong, rotating updraft, a key ingredient for severe thunderstorms. The integration of lightning data fundamentally changed how NWP models were initialized. Instead of relying solely on surface observations, the models were seeded with this lightning information, effectively giving them a jump start. This provided a more accurate representation of the atmospheric instability that was already present, leading to more refined forecasts. The models could then more accurately predict the development and movement of thunderstorms. This process is often described as lightning-triggered initialization. Researchers developed sophisticated algorithms to analyze the lightning data and translate it into meaningful parameters that the models could understand. For example, the number of lightning strikes per unit area, combined with information about their altitude and intensity, could be used to calculate a storm severity index. This index could then be incorporated into the NWP model, further sharpening the forecast. Another important aspect is the use of lightning rate, the number of lightning strikes occurring within a given time period. A sudden increase in the lightning rate, particularly in a specific region, could signal the imminent arrival of a severe thunderstorm. Furthermore, scientists are exploring techniques to use lightning data to improve the forecasting of storm structure. Analyzing the spatial distribution of lightning flashes can help identify the location of mesoscale convective systems, large-scale clusters of thunderstorms. Knowing the size and organization of these systems allows the models to predict their movement and intensity with greater precision. There's also an effort to examine the electrical characteristics of lightning itself. The type of lightning, e.g., cloud to ground, cloud to cloud, can provide clues about the underlying atmospheric conditions. The technology involved is constantly evolving. More advanced lightning detection networks, incorporating data from satellites and even drones, are providing increasingly detailed information. Machine learning is being applied to analyze this data, searching for patterns and relationships that might be missed by traditional statistical methods. This allows for more sophisticated nowcasting, forecasting the weather for the very next few hours, and improved predictions of severe weather events. Ultimately, integrating lightning data into numerical weather prediction isn't about predicting lightning itself. It's about understanding the atmospheric conditions that create lightning. It's about recognizing that lightning is a crucial component of the complex dance between the atmosphere and the earth, and harnessing that knowledge to protect communities from the potential dangers of severe weather. It's a testament to the power of combining observations with advanced computational tools, a partnership that continues to evolve and strengthen our ability to anticipate and mitigate the impact of storms. The electric air crackles. A familiar scent of ozone hangs in the aftermath of a typical lightning strike. But sometimes, Something else lingers, a strange, ethereal glow, a silent hum, and a feeling of intense cold. This is the phenomenon known as ball lightning, and it remains one of the most perplexing and debated aspects of lightning itself. Unlike the dramatic, rapidly discharging bolts we usually observe, ball lightning appears to be a sustained, luminous object, often described as a sphere, though its shape is rarely consistent. Its size ranges from a few centimeters to over a meter in diameter, and its duration can vary from a few seconds to several minutes, an incredibly long time for a phenomenon generated by electrical discharge. The existence of ball lightning has been documented for centuries, with early accounts appearing in written records from Europe and Asia. However, systematic observation and scientific study began in the 19th century, largely driven by reports of its appearance during thunderstorms. Initial accounts suggested that ball lightning was simply a misinterpretation of lightning reflections or unusual cloud formations. Yet, the accounts persisted, and increasingly detailed observations began to reveal a more complex picture. One of the most intriguing aspects of ball lightning is its persistence. While regular lightning flashes are incredibly brief, lasting only a few milliseconds, ball lightning objects can remain visible and even move around for several minutes. This raises fundamental questions about the mechanisms sustaining such a prolonged electrical discharge. Several theories have been proposed to explain this seemingly impossible stability. One prominent hypothesis centers around the creation of a stable, self-contained plasma. Plasma, as we know, is a state of matter where electrons have been stripped from atoms, creating a hot, ionized gas. Lightning generates enormous quantities of plasma, but the standard model predicts that this plasma would rapidly dissipate as the electrical discharge terminated. However, the ball lightning theory suggests that a small, localized region of plasma manages to maintain itself through a feedback loop. The initial discharge, perhaps originating from a stepped leader touching down, would create a spherical shell of plasma. This plasma shell then acts as a conductor, repelling further charge accumulation, and thus preventing complete discharge. The energy released during the discharge is gradually transferred to the surrounding air, primarily through radiative heating and electromagnetic radiation, maintaining the plasma's temperature. Another significant theory, championed by physicist Robert Dixon, focuses on the role of dust particles. Dixon proposed that ball lightning begins with a small discharge, perhaps involving a seed of ionized air. This seed then attracts dust particles, silicates, carbonaceous materials that are readily available in the atmosphere, especially during thunderstorms. These particles act as tiny electrodes, facilitating the continued electron movement within the plasma shell. The plasma then becomes entangled with the dust particles, creating a complex, self-sustaining system. The dust particles absorb and re-emit energy from the plasma, preventing the dissipation of the discharge. Movement is then attributed to subtle electromagnetic forces acting on the charged dust. However, this dust-based model faces challenges. It's difficult to fully explain the initial formation of the plasma seed, and the precise mechanisms of energy transfer between the plasma and the dust remain unclear. Furthermore, The observed speed and direction of ball lightning movement often defies simple explanations based solely on electromagnetic forces acting on dust. More recently, researchers have explored the possibility of resonant absorption within the plasma itself. This theory suggests that the plasma shell interacts with electromagnetic waves, specifically at frequencies related to the plasma's oscillation, creating a self-sustaining loop of energy transfer. The plasma might effectively feed on its own electromagnetic radiation, maintaining its temperature and luminosity. This idea is supported by some spectroscopic observations, which have detected broadband electromagnetic radiation emanating from ball lightning objects. The dissipation of ball lightning is equally mysterious. Unlike regular lightning, which abruptly ceases when the stepped leader retreats, ball lightning doesn't simply vanish. Instead, it often fades away slowly, sometimes accompanied by a faint, cool glow or a brief, sharp sound. Proposed mechanisms for dissipation include gradual radiative cooling, where the plasma loses its internal energy to the surrounding atmosphere, or the gradual settling of dust particles, disrupting the resonance mechanisms. Some observations suggest that ball lightning may eventually merge with regular lightning discharges, effectively transferring its energy back into the larger electrical system. The final stages of dissipation are frequently marked by a pop or crack sound, potentially generated by rapid ionization in the surrounding air as the plasma's energy is abruptly released. This event is often observed just before the final fading of the ball lightning object. Despite decades of research, the precise nature of ball lightning remains elusive. The available observational data is often fragmented and inconsistent, making it difficult to definitively test any particular theory. The phenomenon's transient nature and the challenges of directly studying it in situ further complicate the investigation. Nevertheless, the ongoing research into ball lightning continues to provide valuable insights into the complex processes occurring during electrical storms and the fundamental physics of plasmas. It stands as a compelling reminder that even the most familiar phenomena can hold profound scientific mysteries. The study of lightning, surprisingly, began not with sophisticated instruments and mathematical models, but with careful observation, a practice dating back to the earliest humans. Ancient civilizations across the globe recognized lightning as a powerful and potentially destructive force, and their initial responses were rooted in respect, fear, and attempts to appease the elemental spirit they believed was responsible. Records from ancient Mesopotamia, dating back to the 3rd millennium BC, describe elaborate rituals performed to ward off lightning strikes. Offerings of livestock, precious objects, and even human sacrifice were sometimes employed. Similarly, the ancient Greeks, particularly philosophers like Thales and Empedocles, developed theories about the nature of lightning, suggesting it was a fiery spirit or a manifestation of divine wrath. These early ideas, though lacking a scientific basis, represented a crucial first step, acknowledging the phenomenon's existence and attempting to understand its origins. The first systematic scientific investigation of lightning emerged in Europe during the 18th century, largely driven by the burgeoning field of electricity. Benjamin Franklin, perhaps the most famous figure in early lightning research, is, of course, inextricably linked with the story. His famous kite experiment in 1752, though often depicted dramatically, was actually a carefully planned and executed demonstration. Franklin wasn't attempting to catch lightning, as popularly portrayed. Instead, he was investigating the relationship between lightning and static electricity. He suspected that lightning was a form of static electricity, a theory supported by his experiments with Leyden jars, early capacitors capable of storing electrical charges. He famously demonstrated that a thunderstorm cloud could generate a static charge, which then discharged through his kite, creating a spark that he observed by holding a metal key attached to a wire. While the experiment itself was fraught with risk, and Franklin suffered several minor injuries, it provided compelling evidence for a connection between atmospheric electricity and lightning. Following Franklin's work, the 19th century saw a flurry of activity, primarily focused on understanding the electrical properties of lightning. Scientists like Charles Augustin de Coulomb, through his meticulous experiments with electrostatic forces, provided a quantitative framework for understanding the interactions between charged particles, a foundation that would eventually lead to a more complete understanding of lightning discharge. The development of the telegraph in the early to mid-1800s spurred further interest in lightning, as the technology relied on the transmission of electrical signals along wires, often subjected to disruption by lightning strikes. Engineers began to study the effects of lightning on telegraph lines and develop methods for protecting them. However, accurately measuring the characteristics of lightning remained a significant challenge. Early attempts to determine the current and voltage of lightning discharges were hampered by the phenomenon's fleeting nature and the lack of sensitive instruments. The breakthrough came with the development of Roger Thomson's rotating spark gap hygrometer in 1882. This ingenious device, housed in a large tower, employed a rotating wheel with a gap between its edges. When a lightning strike occurred, the ionized air around the wheel created a conductive path, and the wheel would rotate, providing a direct measurement of the lightning current. Thomson's instrument allowed scientists to record the duration, current, and voltage of lightning strikes with unprecedented accuracy. The 20th century witnessed a dramatic expansion in lightning research, fueled by advancements in electronics and instrumentation. The development of microwave radar in the 1950s provided a revolutionary new tool for detecting and characterizing lightning. Radar systems could detect the radio waves emitted by lightning discharges, even through heavy cloud cover, allowing for real-time tracking of storms and the estimation of their intensity. Simultaneously, the development of photoelectric detectors, which could sense the light emitted by a lightning flash, provided another valuable method for observation. These advancements, coupled with the increasing use of computers, enabled scientists to collect vast amounts of data and develop sophisticated models of lightning formation and propagation. Throughout the latter half of the 20th century, researchers began to focus on the atmospheric conditions that trigger lightning. They realized that thunderstorms are driven by strong updrafts, rising columns of warm, moist air, and that these updrafts can create highly charged regions within the clouds. Experiments using aircraft equipped with probes and sensors allowed scientists to directly measure the electric fields and potential gradients within thunderstorms, providing critical insights into the processes that lead to lightning initiation. This research also revealed that there are different types of lightning, categorized by their appearance: cloud to ground, intra-cloud, and cloud to cloud, each associated with distinct atmospheric conditions and discharge mechanisms. Furthermore, sophisticated computer simulations began to model the complex interactions between the atmosphere, the charged particles, and the electric field, gradually building a picture of how lightning actually happens. Today, lightning research is a highly interdisciplinary field, drawing on expertise from meteorology, physics, electrical engineering, and computer science. Networks of ground-based lightning detection sensors, combined with satellite observations and advanced radar systems, provide a global eye on thunderstorms. The data collected is not only used for operational weather forecasting, but also to improve our fundamental understanding of this powerful and beautiful natural phenomenon. The story of lightning research, from ancient observations to modern-day monitoring, is a testament to human curiosity and our persistent desire to unravel the mysteries of the natural world. The familiar crackle and flash of lightning, a spectacle we often take for granted on Earth, has become a surprisingly vital tool in the grand, ongoing quest to understand life beyond our planet. While lightning itself might seem a purely atmospheric phenomenon, researchers are increasingly considering it as a potential key to discovering evidence of life on other worlds. The idea stems from the realization that lightning, the most energetic event occurring naturally on a planet, dramatically alters the chemical composition of the atmosphere, creating fleeting, yet potentially detectable, signatures. Our understanding of lightning formation on Earth has dramatically expanded in recent decades, fueled by sophisticated sensors and advanced computer modeling. We now know that the process isn't simply a random discharge. It's a complex chain reaction involving ice crystals, supercooled water droplets, and atmospheric electric fields. These conditions, particularly prevalent in cloud formations like those found on Jupiter and Saturn, are arguably replicated in many other planetary atmospheres. These environments can generate immense electrical potentials, triggering lightning strikes with astonishing frequency. This realization opens a compelling avenue for astrobiology, the study of life in the universe, focusing on what these atmospheric alterations might reveal. The core principle revolves around biosignatures, indicators that suggest the presence of life. Traditionally, we've looked for biosignatures on other planets through direct observation, a green, blue, or orange planet hinting at oceans or plant life. However, the sheer vastness of space and the challenges of interstellar travel make that approach incredibly difficult. Atmospheric studies, specifically the detection of altered gases, offer a more practical and arguably more sensitive method. Consider Mars, a planet long suspected of harboring past life. The Curiosity rover and the Perseverance rover have been diligently analyzing the Martian atmosphere, and a particular gas, phosphine, has generated considerable excitement. Phosphine is a gas that's almost exclusively produced by biological activity on Earth, primarily by microbes living in oxygen-poor environments. While the detection of phosphine on Mars remains controversial, with some scientists arguing that geological processes could potentially produce it, it represents a powerful demonstration of how lightning could serve as a catalyst for discovering potential biological signals. The mechanism is this. Lightning strikes can break apart complex molecules in a planet's atmosphere, creating simpler ones. These reactions can then produce gases that wouldn't naturally exist in significant quantities without biological influence. For example, a lightning strike could transform methane, a relatively stable gas, into isoprene, a volatile organic compound produced by plants and some microbes. The concentration of these newly formed gases, particularly if they're at levels that contradict existing atmospheric models, could serve as a strong biosignature. Saturn and Jupiter present particularly intriguing targets. These gas giants possess incredibly dynamic atmospheres, characterized by towering thunderstorms that dwarf anything seen on Earth. These storms generate colossal lightning events, far more intense and frequent than those we experience on our own planet. The sheer scale of these electrical discharges raises the possibility of producing distinct atmospheric alterations that could be detected remotely. Scientists are developing techniques to analyze the light reflected or emitted from these giant planets. When lightning occurs within these turbulent clouds, it doesn't simply produce a flash. It interacts intensely with the surrounding atmospheric gases. This interaction can create spectral signatures, unique patterns of light absorption and emission, that could reveal the presence of specific molecules, including those produced through biological activity. Advanced spectrometers, both ground-based and orbiting, are being designed to analyze these subtle shifts in light. Beyond the gas molecules themselves, researchers are also exploring the potential impact of lightning on aerosols, tiny particles suspended in the atmosphere. Microbes can produce organic compounds that contribute to the formation of aerosols. Lightning could then trigger chemical reactions within these aerosols, creating new compounds that are detectable. The detection of these newly formed aerosols, coupled with evidence of altered gas concentrations, could paint a much richer picture of potential biological activity. The study of exoplanets, planets orbiting stars other than our Sun, is also benefiting from these lightning-focused investigations. While directly observing lightning on exoplanets is currently beyond our capabilities, scientists can model the atmospheric conditions based on the planet's size, mass, and distance from its star. These models can then predict the likelihood of lightning strikes and the resulting atmospheric changes. Furthermore, future telescopes, such as the James Webb Space Telescope, will have the power to analyze the atmospheres of some exoplanets, searching for these telltale signs of lightning-induced chemical transformations. It's important to acknowledge that this is a nascent field of research, and many challenges remain. Distinguishing between biological and geological processes that could create similar atmospheric signatures will be incredibly difficult. However, the potential rewards, the possibility of detecting evidence of life on another world, are enormous. Lightning, once merely a spectacular display of atmospheric power, is now viewed as a potentially revolutionary tool in the search for extraterrestrial life, a silent messenger carrying clues from the vastness of space. The next generation of space telescopes and atmospheric probes will undoubtedly play a crucial role in unlocking its secrets. If you're still awake and enjoyed this exploration of lightning's raw power, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds one peaceful night at a time. The storms have passed and the energy has settled. Let your thoughts drift, calm and unhurried like clouds across the darkening sky.